In this problem we have a microscope, and we're told that the focal length of the objective is 0.5 centimeters, the focal length of the eyepiece 2.5 centimeters, the length between the two lenses is 14 centimeters, and if you're looking at a speck of dust just with your naked eye, it subtends an angle of 2.1 times 10 to the minus 5 radians, and we want to find the angle subtended if we look at it through the microscope, given that the normal point of your eye is 25 centimeters. So we draw this microscope configuration. So we have the objective here, the eyepiece here that you put your eye to. So I've drawn the length between the two is L. We have our focal length of the objective, our focal length of the eyepiece. And if we have an object out here that we're looking at, this piece of dust, it's got its length P. It forms an image at the focal point of the eyepiece. That's where your image is formed. So the image forms here, that's our Q, and that's basically all we need to know to figure this out. So to start, we want to do our magnification equation. We're looking for M equals theta prime over theta. So, and because we're looking for theta prime. Now, we don't know magnification, but we do know theta. So, work backwards, we need to find magnification. In this case, magnification, total magnification is going to be equal to magnification from our eyepiece times magnification from our objective. We have that from our formula sheet. Our total magnification is equal to the product of the two magnifications. So we need to figure out what each of these is. Magnification of the eyepiece for a microscope is equal to n, the near point, divided by the focal point of the eyepiece. Okay? So, let me just write that as big E, like the rest. Okay, now magnification of the objective is the same as it always is, minus Q over P. So a regular one. Okay, so our total magnification becomes this times this. So we have minus N Q over focal point of your eyepiece times P. Now, we know N. We can figure out Q because we know this distance L and FE. Okay, so we can actually figure out Q. We do know Q. We don't know P, and we know FE. We need to figure out P to get our magnification. Once we get our magnification, we can figure this out. So we need to figure out P just using our regular 1 over our thin lens equation. 1 over F equals 1 over P plus 1 over Q. Okay? So we solve for P. P equals 1 over F plus 1 over Q inverse. Okay, so Q, I'm going to show you right now, is just L is going to be Q plus FE. Okay, so L equals Q plus FE. So Q equals L minus FE. Okay, so I plug everything I need to know in here. So 1 over F is, this is the focal point of your objective. Make that clear, this is your objective focal point, because you're finding out if this is P for this, it's Q for this lens. So it's your focal point of your objective. So we are going to use both focal points here. So 1 over FO is 0.50 centimeters minus 1 over Q, which is L minus FE. L is 14 centimeters minus FE is 2.5 centimeters. Over that. Inverse. So P equals 0.5227 centimeters. 0.5227 centimeters. Now we know P. We can plug all that into our magnification equation and figure out what our actual magnification is. So let's do that. So M equals minus N, your near point, 25 centimeters. Q is, well, we didn't actually figure that out. We'll write this down, L minus FE. So 14 centimeters minus 2.5 centimeters. That's just 11.5 centimeters. So I'm going to write that down as 11.5 centimeters. Divided by focal length of our eyepiece, 2.5 centimeters. Times by our P that we figured out to be 0.5227 centimeters. We get a magnification of 220.0115. Okay? Now, all we have to do is find our theta prime, which is equal to magnification times theta. So we have our magnification to 20.0115 times our theta of 2.1 times 10 to the minus 5 radians. So we get the angle subtended of our image becomes 4.6 times 10 to the minus 3 radians. And that is your final answer.